Hey everybody, this might be a little bit of a rambly video. I got back from Japan a couple days ago, still pretty jet lagged, so if I'm a little more rambly than usual, please forgive me that. But wanted to talk briefly about this video that was posted to Discord. It's titled please_fix.mp4. Clever title for something that they want fixed, I guess. Let's take a look. So basically, what this user has is in the StarCraft UI, you can see that they actually have names that have different colors in them than the default. Right? Different names, also some symbols here, but they have these different colors in the UI. Now, what they're pointing out in the video is that when they host a game with those codes using crownlink, it doesn't actually show up as a game that's available for others. Now, why is that? Well, let's first talk about what's happening under the hood here, why this is working to begin with. And to do that, we have to go back to a little bit of history and a little bit of technical detail around how text encoding works. Now, what's text encoding? Well, when you have a character on your screen, that character is actually a number under the hood. You're probably aware everything in computer is binary, so everything is a number. And that number corresponds to a specific letter. Right? Now, which letter does it correspond to? Which character? What does it mean? Well, older games like StarCraft used something called ASCII. In fact, ASCII was in older operating systems pretty common. There was a few other alternatives. But when you look at ASCII, you can see we have all the different characters here, like all the different letters, and each letter corresponds to a binary value that's held in 1 byte of data. And that 1 byte of data corresponds to a decimal number. So you can see here the letter Q is actually a decimal number of 121. Now these other columns are just the same representation of that in octadecimal and hexadecimal. Hexadecimal we see most common. So this 121, it would be displayed by a hex editor as 51. So that's equivalent, right? So this 51, this 121, they equal 1 byte that corresponds to the letter Q. Now, one thing you'll notice here is that in this table in Wikipedia here, the lowest binary character here is actually 20, which is a space. As you can see, no visible glyph. Why is that? What are the numbers under 20? Well, below 20, there are so-called control characters, right? The control codes were used for transmission and a few other things, but they don't actually correspond to a specific character, right? We've got a null byte here, which is the 0. We've got a start of heading. We've got start of text, end of text. You can see there's a bell character that is an alert character. We've got a character that corresponds to backspace, a horizontal tab, right? So these are actually part of the ASCII standard. Well, what Blizzard did is they used these characters as kind of a markup language for text. So when you have a string of text, if we look at like a hex editor as an example here, let's say we have a string of text that is my name, Jesse here. You can see the numbers that correspond to each of those characters here. What Blizzard did is they let you use, or internally in their UI, they used these control characters, which don't actually correspond to real letters, as a way to dictate text. As an example, in the lobby, here is a reference that shows what they correspond to, right? So 0x2, or the number 2 in binary, corresponds to this kind of blue color, or purple, or whatever you want to call that. Number 7, remember that was the bell character, that corresponds to red, right? So when you have that character, if you had 07 for this character, right, what that would do is in the lobby, that would turn this red. Now, there's two problems with that. First of all, the color codes, as I've been calling them, that are used in the lobby differ from the codes that are used in the game. Right? You can actually see in the Cosmonarchy source code here There was some reverse engineering done to figure these out, right? So the lobby text color, you can see these colors here. There's only a handful of them. And in game, there's quite a few more, right? And they don't line up, right? Red was 07 in the lobby. In game, 07 corresponds to green. Right, so your name color might not actually reflect correctly. The other thing is, notice that this top one is special, right? 0x01 is called revert. What that does is it reverts the text to the previous color code that was listed. Right, so if I go back to my hex editor here, and I have 07, which again makes it red, right? And then let's say I had 04 here, which makes it light green, and then I did, let me fix this a little bit, and then I had 01 here. What would happen is, it would, as the games are reading through, it would say, okay, I'm gonna make it red, and then I'm gonna play the G or the J. I'm gonna post the J, print the J, and then 04, I'm gonna go ahead and make it green, and here's a couple more characters, and then I'm gonna revert, which means it's actually gonna go back to the color before this one. So it's actually gonna go back to red, and then the last E would be red. Right, so that's how that revert character goes. Now you might be wondering, what happens if you have a revert character at the beginning? Well, the answer is the game doesn't know what to do about it if you're in the lobby. So in the lobby, if you do that, you're actually going to get black text. It's going to render the outline of the text, but it won't know what color to actually draw it, so it's actually just going to draw it in black. Now in the game, though, there are certain situations where it will kind of use the last color used. So you may find that in the game, sometimes that has a different effect than it does in the lobby. Because again, the lobby and the actual game work a little different as far as the color codes go. So that's problem number one. Problem number one is the color codes don't line up and the revert has kind of a special effect. Problem number two is, how do you actually get one of those codes in the name of your character? Because although when you're programming, you can just hard code those in, no problem whatsoever, you can't exactly type a 02 character. If you hit the number 2 on your keyboard, keep in mind, that's not going to give you a numerically 2 character, right? The number 2 that you type on your keyboard is actually this binary, which is 62, right? So you type 2, you're going to get a 62 in memory. So how do you actually get a 2 or a 1 in memory? Well, the trick that's being used here is exploiting the difference in text encoding. I mentioned ASCII is just one of the ways to do text encoding, but you've probably realized, of course, there are a whole lot more characters than 255 that might need to be drawn by a computer. And you can't actually display more than 255 with 1 byte of data. So back in the day, this group came up with what's called the Unicode standard, which allows you to use multiple bytes, basically a bigger number, to display the actual text. So it lets you use up to 4. So 2 bytes would be a 16 bits. So you've got UTF-16, and then 4 bytes would be 32 bits. So that's UTF-32. Now the NTFS file system, which, by the way, just as a reminder, StarCraft came out before Windows XP, which was the first version where NTFS was commonly used. So this is a little bit of unknown behavior to the original developers. But when NTFS came out, it uses UTF-16 for file names. So file names are actually encoded with 2 bytes per character. So if I actually grab this file name just as an example, or maybe a better example, if I go back to Notepad++ here, and I make this file name with this character in it, right? And then I save that, and I save it in UTF encoding, if I pull open that UTF-16 file in my hex editor, what you're going to see is that even though it's only got one character in it, or it's actually got two because I've got two of these Y's with the umlaut on it, even though I've only got two characters, we actually have 4 bytes here, right? Because each character is 2 bytes of data. But here's the thing, StarCraft doesn't understand UTF-16. So it's actually going to interpret these two characters, or these 2 bytes rather, that are a single character. You can see it's a single Y with the umlaut there. It's actually going to interpret that as 2 separate characters. So we have a 78, which is actually 120 decimal, which equals a lowercase x. And then we have a 01. And remember, 01 is that fancy revert byte, right? So in the lobby, that 01 is going to cause the text to be black. In the game, that 01 may cause the text to be a different color depending on the game state, right? So the game misunderstands this UTF-16 as 2 separate characters, one of which is this 01. And if we had a different character that had a different number in here, like a 02, for instance, again, kind of the same thing. The UTF-16, here you can see that's this, whatever character this is, might get interpreted by the game as a X and a 02, which again is going to be a different color text. Okay, so that's how that is working. Why doesn't it work in crownlink? Well, again, it comes down to text encoding. So crownlink actually will again use a different kind of encoding called UTF-8. Now, why UTF-8? Well, most modern systems actually use UTF-8 instead of UTF-16 because it actually is more flexible. I mentioned UTF-16 uses 2 bytes or 16 bits for every character. UTF-8, so that's UTF-16. UTF-8 actually uses anywhere between 1 and 4 bytes. So in other words, it only uses more bytes if it needs to. So that's more efficient on memory, on transmission, on basically everything, right? How does it accomplish that? Well, remember that a byte is 8 bits. You've got 8 ones and zeros. That's a byte, right? So how is the computer supposed to know if, as it's reading through the bytes, if the next character that it's reading is 1 byte, 2 bytes, 3 bytes, or 4 bytes? Well, it knows that because UTF-8 encodes how many bytes are in the character in the first 2 bits, or 1 or 2 bits. If the first bit is a 0, then it's a single character, right? So this could be 0, if I go back to the binary here, I can just grab anything here. So for instance, like an R, right? So I grab this. This, and you can see actually here in the ASCII table, these ASCII codes are only 7 bits long, right? So this binary number here, which equals 122, which equals an R, right? And it knows that it's just 1 byte because it starts with a 0. Now, what if it starts with a 1? Well, if it starts with a 1, then the next number or numbers tell it how many digits are following it. So if it's a 2-digit UTF-8 character, or 2 byte UTF-8 character, it will have a single 1. So we've got 2 ones there. It's going to be a 2 byte character. So it's going to be, something like this. And then it's got the next character, and the next byte will have a 1 and a 0 to say, hey, this is not the first byte in the sequence. It's a follow-up. It's a continuation. Right? So now this is 1 character. Now if there's a character that's 3 bytes long, you can imagine it goes like this, right? So there's 3 ones now. And then the same thing, 1, 0, 6, 6, 7, right? And the same thing with 4, right? It's going to be 4 bytes long. So where does that run into trouble with UTF-16? Well, you have some UTF-16 characters that do not translate properly to UTF-8. As an example, if I pull open this character, right? This is a character that Pronogo was using for a username for a little bit, wasn't working with crownlink. Well, if we look at how this character is displayed in UTF-16, it is 00DB. Right, 00DB. Now, what does that look like in binary? If we go and we get rid of 00DB, see, there's that character, right? Same character. If we look at that, that binary is 1101111. So if we reference back to how UTF-8 works, the UTF-8 parser is going to look at this character or look at this byte, and it's going to say, oh, this is part, because it's got 1 at the beginning, this is part of a 2-byte character. But the byte before it, this is in little endian, so it's the byte before, won't go into that right now, but the byte before it is a 0, which is not valid, right? So what's going to happen is the UTF-8 parser is going to say, this is invalid UTF-8, and it's not going to handle it. So that's what happens. The server is actually rejecting this because it doesn't know how to handle this character. This is valid UTF-16. It is not valid UTF-8. And converting between the two is not a trivial matter. So that's something that I'll need to look at figuring out. But that's today why if you manipulate the file name or use an alt code to get a UTF-16 character, or if you're getting outside of the normal ASCII range, and if you're trying to get that into the server, it won't know how to handle it, right? And it'll get discarded. So those are the two problems that we have right now. Hopefully that technical explanation made sense. Hopefully you found it interesting. If you don't find it interesting, then definitely don't subscribe, because this is the kind of stuff that I like doing a deep dive on. But if you did find it interesting, well, hopefully I'll be putting out more videos in the future. I guess I'm doing the YouTube thing now, huh? And hopefully in the near future, I'll be working on some updates to crownlink to kind of resolve this. But that's what's going on under the hood. I need to figure out a way to properly convert UTF-16 to UTF-8, and we'll go from there. All right, well, that's all for now. Thanks again for watching. See ya.